Hi all. Today we are discussing about electrocyclic reaction, which is a part of pericyclic reaction. So before going to further detailing about electrocyclic reaction, I'll introduce you into pericyclic reaction. So what these reactions means, we'll see. Okay, from the name itself, we can see peri in Greek means around. So these are the reaction which will happen around the molecule in a cyclic manner. And these are the different characteristics of a pericyclic reaction, which will proceed without the help of an intermediate. And normally in organic reaction, we can see the reaction will proceed either by the formation of carbocation, carbanion, or carbon radical. But here in pericyclic reaction, we cannot see any such intermediate. Instead, it will pass through a transition state, which will be a cyclic one. For example, consider going from a reactant to product in a pericyclic reaction. There will be a transition state in between reactant and product that will be a cyclic one. Okay. And this reaction will be concerted. Concerted means here both bond breaking and bond forming will happen at the same time. To explain both these points, I'll give you an example of butadiene molecule. Suppose this molecule is participating in pericyclic reaction. We'll get a molecule like this. How this bond form, how this molecule form, we'll see. In reactant, you can see these two bonds. But in product, you cannot see these two bonds here, right? But instead, you can see two new bonds, which is not there in the reactant. So how the transition happened from reactant to product? It happened through a cyclic transition state. So to draw this transition state, first we'll draw the bonds which is not being changed in the reaction. It is these three bonds we'll draw like this. Now, look at the bonds which is being broken. These two bonds. That we'll draw like this. Now we are using dotted lines because these bonds are being broken. Okay. Now we'll draw the bonds which are being formed. That is these two bonds. How we'll draw this? We'll draw it like again dotted lines because these bonds are not fully formed. It is forming only. And this is, as you can see, a cyclic transition state. It's transition from reactant to product. Okay. And what is concerted means? Concerted means here these two bonds are breaking, these two bonds are forming. These, if you look at cyclic transition state, we can see both bond breaking and bond forming is happening at the same time. This is what is mean by concerted. Okay. Now we'll look at the conditions for a pericyclic reaction. There are two conditions. Either it can be thermal. Thermal we will denote by delta or by photochemical, which we will denote by H nu. So there are two conditions. Either it is thermal or photochemical condition. And there are different type of pericyclic reaction like electrocyclic, sigmatropic, cycloaddition, and in reaction. In this lecture, we'll focus only on electrocyclic reaction. So what is electrocyclic reaction? It is basically the cyclization of conjugated polyene system. So first we want to know what is conjugated polyene system means. Polyene system means any system which containing two or more than two pi bonds. Okay. So we'll take two examples here. We'll take butadiene and the end product will be cyclohexadiene. Here, hexatriene. So we'll take these two molecules, butadiene and hexatriene. These two are an example of polyene system. Because why? Both these molecules containing, this containing 2 pi bonds, this containing 3 pi bonds. So both this containing 2 or more than 2 pi bonds. So these two are an example of polyene system. Now, what is conjugated mean? Conjugated means a molecule which containing alternate single and double bond. So it will look like this. So this is what conjugated means. Here, butadiene is a conjugated because this contains alternate single and double bond. Hexatriene is also conjugated because this also contains alternate single and double bonds. Okay. Now, electrocyclic reactions means cyclization of conjugated polyene system. So how the electrocyclic reaction will happen in this molecule? It will happen by cyclization. This bond will move here and this bond will move here. Here in this molecule, this bond will move here, this bond will move here, this bond will move here. Okay, this is how electrocyclic reaction will happen. And for any system which is participating in electrocyclic reaction, we will categorize it as either foreign system or foreign plus system. How will we categorize this? That we are seeing the next. Okay, so we want to characterize any molecule as either as foreign or foreign plus 2. How we'll do this CRC? So N can be 0, 1, 2, 3. If it is foreign, 0 means it will be 0, so there is no electron, so there is no reaction. But N is equal to 0 here means foreign plus 2 means 2 electron. If N is equal to 1, foreign means 4 electron. If N is equal to 1, foreign plus 2 means what? 4 into 1 plus 2, it will be 6 electron. If N is equal to 2, that means foreign means 8 electron. Foreign plus 2 means 10 electron. If N is equal to 3, foreign 12, and here it will be 14. So from this we can see any system which contain either 4, 8, 12, etc. Next will be plus 4, 16, yeah, etc. This kind of electron will call as foreign system. So any system which contain 4, 8, 12, 16 will call foreign system. And any system which containing either 2, 6, 10, 14, etc. electrons will called foreign plus 2 system. So this you keep in mind how to find whether it is foreign system or foreign plus 2 system. Okay, and this reaction will happen either through thermal or photochemical condition. And this electrocyclic reaction can be ring closing or ring opening reaction. So how the ring closing will happen, we'll see by taking the hexatriene as an example. So for that, we'll draw first hexatriene molecule. Now again, how the electrocyclic reaction will happen? This bond will move here, this bond will move here, this bond will move here, right? So before writing product, first we'll write the cyclic transition state. So first we'll draw the bonds which are not being changed during the course of reaction. So that is these bonds which are not being changed. Now we'll draw the bonds which are being broken. This bond is being broken, this bond is being broken, this bond is also being broken. Now we'll draw the bonds which are being formed. So this is forming, this is forming, this is also forming. So this is the transition state, right? Now we'll write the product. How the product? Again, we'll draw the bonds which are not being changed during the course of reaction. Now here a bond formed, here also a bond is formed, here also a bond is formed. So this is the reactant and this is the transition state, this is the product. Here you look at these two molecules. This is a kind of open molecule, right? And this is closed. So we are going from open to closed. So this type of electrocyclic reaction is called ring closing. So it is called ring closing. While going from here to here, it is called ring closing. If this same reaction is happening from here to here, it will call us ring opening. How? I'll show you by taking this as reactant. Now in this first, here it is the product. Now we'll take this molecule as a reactant. Okay. It took this molecule. Now we'll do electrocyclic reaction in this molecule. How electrocyclic reaction will happen? This bond will move here, this will move here, this will move here. So how the transition state will come? It will be like this. Now this bond is being broken, this bond is being broken, this bond is being broken. And here this is formed, this is forming, this is also forming. Okay. And product will be, again, we'll first draw the bonds which are not being changed. A new bond is forming here, here, and here. Now compare. Both this molecule and this molecule is equal, right? So from this example, we can see if from one molecule we are starting and reaching at another molecule by ring, here it is ring closing. If we conduct the reverse reaction, it will be ring opening. So it is ring closing. This one is ring opening reaction. Okay. And next point is it will pass through a cyclic transition state, as you can see here. It is passing through a cyclic transition state. Okay. Now we need to look at the stereochemistry of the electrocyclic reaction. For that, we just need to remember only one equation, which is 4n delta cone. We need to by heart this. From this, we can derive all other three relations. You just remember 4n delta cone. I'll explain later what this cone and this means. Okay. But as of now, you just remember this 4n delta cone. So there are three other relations. I'll show you how to derive all other three from this single equation. Before that, you remember either there can be foreign system or foreign plus two system. Either there can be thermal condition or HNU condition, or either these all terms will come in pericyclic and also electrocyclic. Okay, so here I am explaining about electrocyclic reaction, right? So now I am explaining how the terms will be in electrocyclic reaction. So now what will come? Cone will come, this will come. And whatever happening in foreign system, it will be opposite to what is happening in 4n plus 2. It is a kind of opposite tree. You just remember that. Okay. And whatever happening in thermal condition will be opposite to photochemical. Whatever is cone, it is opposite to this. So cone and this is kind of opposing rotation. Okay. First you remember this. Now we will derive other three relation. For that, we will see. So we are deriving the other relations. So there can be two type of systems in electrocyclic. They are either they can be foreign or they will be foreign plus two, right? Either they will be foreign or there will be foreign plus two. Now there is two type of condition. Either the reaction will happen through thermal or photochemical. We already know foreign delta. We already by heart here foreign delta cone. So that means in foreign delta it will be cone. So if foreign delta is cone, here I told you whatever is happening in foreign and whatever happening in thermal, HNU will be the opposite one. So if it foreign thermal condition is cone, then HNU condition usually be opposite of cone. It will be this. Now we got one more relation. Now look at the foreign plus 2 delta. I told you foreign and foreign plus 2 is kind of again opposite. So here foreign delta is cone means foreign plus 2 delta will be opposite of cone, which will be this. Okay. And foreign plus 2 delta this means foreign plus 2 HNU will be what? Opposite of this, which will be cone. So it is so simple. You will just remember this foreign delta cone. From that, you will derive all other three relations. So we already learned, right, how to derive this. Now we'll fill this table. You know, foreign delta is cone. That we by hearted, we already know foreign delta is cone. Now, if foreign delta is cone, foreign HNU is this. Okay. If foreign delta is cone, then foreign plus 2 delta is what? Opposite of cone. It will be this. And if foreign plus 2 delta is this, if foreign plus 2 HNU will be cone. Okay. So we learned so these selections rules are called Woodward Hoffman rules. Okay. So we learned Woodman-Hoffman selection rules for electrocyclic reaction. Now we look at the stereochemistry of electrocyclic reaction. How the stereochemistry, how the product will be. For that, again, we'll take the butadiene molecule. We know if the electrocyclic reaction happened here, then the product will be this bond will move here, this bond will move here. The product will be like this. A new bond is being formed here, a new bond is being formed here. This will be the product. Now we are looking at the stereochemistry. If you are looking at the reactant molecule, so this is the reactant, this is the product. If you are looking at the reactant, 4 carbon atoms are there. And all these carbon atoms are sp2 carbon. So this is a planar molecule. But look at the product. Here, this carbon and this carbon. These two carbon are sp2 carbon. But look at this carbon and this carbon. This carbon and this carbon, they are sp3 carbon. That means we need to mention the stereochemistry of these two bonds in product. How we will determine the stereochemistry of the product is what we are going to see in the next few slides. Okay. Suppose a molecule like this participated in electrocyclic reaction. Here the electrocyclic backbone is this one. We know what product we will get from this, right? It will form a product like this, that we know. But we don't know the stereochemistry of these two bonds that we are going to see in the next. Okay. So this will undergo electrocyclic either in thermal or HNO condition. And we'll get a product like this. And here there are two bonds. Here two more bonds are there because carbon valence is 4. So two more bonds are remaining to mention. Here in reactant also we can see one bond is here, one bond is here. But all these bonds are in plane of the paper. It is a planar molecule only. But here, if you are mentioning other two bonds, one will be towards us, other will be opposite to us. One will be towards and one will be away from us. Right? So suppose there is a substituent here and substituent here also. There is hydrogen. If one substituent is coming here and hydrogen is coming here, where will this one, where X will come? Here or here? That is our doubt. If it is coming here, this will be a cis product. If it is coming here, it will be a trans product. So what product we will get? That is our question. Okay. What will be our product? Whether it will be cis or trans is our question. So how to find the stereochemistry of the product? For this, it is a two-step process. First, we need to find the overall stereochemistry of the reactant. Okay. Second step is we need to find through selection rule, cone or disc, which rotation is happening is what we need to find using Woodward-Hoffmann rule. So by doing these two steps, we will get whether cis product is forming or trans product is forming. To explain this, I'll take a molecule. So first I'll explain how to determine the overall stereochemistry of the reactant. First, I'll discuss this step. For that, I'll take a few reactant molecule. Suppose here I'll take the same molecule that we discussed now. To look at the stereochemistry, overall stereochemistry of the reactant, we need to look at two bonds. This bond and this bond. Okay. Because after the reaction happened, reactant product will be like this. So that time we need to mention the stereochemistry of this bond. So before that, we'll look at the stereochemistry of these two. That means if this bond is cis, what is the stereochemistry of this bond? That we are going to see here. Look at this bond. This is kind of opposite to each other. So this is what? You already know, right? In double bond, if both substituents are on the same side, it is called cis. Suppose a double bond, one substituent this side, other substituent is this side, then it is called trans. So here, if you look at this molecule, you can see one substituent is this side, other one is that side. Here it is hydrogen. Here hydrogen. Normally you will not mention hydrogen during the reactions. Okay. So here one bond is towards this side and other is kind of opposite. So this bond is trans. And look at this bond. Here also one bond is through here, one bond is through here. So this also trans. So both bonds are trans. If both bonds are trans, then what is the overall stereochemistry of the molecule is what we need to find the next. For that, you just remember if both bonds are cis, if first bond is cis, second bond is also cis, overall stereochemistry of the reactant is cis. If first bond is trans, second bond is also trans, then overall stereochemistry of the bond is cis again. Okay. Don't make mistake here, okay? If both bonds are cis, then overall stereochemistry is cis. And if both bonds trans also, stereochemistry is cis. Now, If one bond is cis and next bond is trans, that means stereochemistry of the reactant overall is trans. This we need to remember. If one bond is cis, one is trans, then the overall stereochemistry is trans. Otherwise, if both bonds are cis, then it is cis. Both bonds are trans, then also it is cis. So here you look. Both bonds are trans. That means the overall stereochemistry is cis. We'll take one more molecule. Now we'll look at the hexatriene molecule. Here look, one bond. Suppose the bond is like here it is CH3, here it is CH3. Here you look in this bond. Now which bonds you look at? You need to look at this bond and this bond. Okay. Because at the end product, we need to mention the stereochemistry of these two carbon. Because all other these four carbon, even after reaction, it will be sp2 carbon and it will be in the plane of paper, these four carbon. But these two carbon will be, after reaction, will convert to sp3 carbon. So we are going to look at the stereochemistry of these two bonds, whether it will be cis or trans. First, look at this bond. So in this bond, one substituent is this side, other substituent also in the same side. So this is what? This is cis. Now look at this bond. Here one substituent is this side, the other substituent is in opposite side, right? So it is trans. So the overall stereochemistry is what? If one is cis, the other one is trans, it will be trans. Now the overall stereochemistry of the reactant is trans. So now we learned how to determine the overall stereochemistry of reactant. We'll go to the next step. How to find whether cone rotation is happening or disrotation is happening in the molecule. For that, we already learned the selection rule. I told you, we just need to remember one relation, 4 and delta. 4 and delta cone. Yes, we just remember this 4 and delta cone. And if 4 and delta is gone, we'll find, like I mentioned earlier, we'll find out other 3 relations from this single relation. So suppose we already determined the starting stereochemistry of the reactant molecule, and that time we got cis. And depending upon whether cone or disrotation is happening, we will get the stereochemistry of the product molecule. And now I'll explain what this cone and this means. Cone means, first we'll take cone. Cone means change in stereochemistry. So this will be what? I told you whatever is happening in cone will be opposite in this. If in cone change is happening, this will be no change in stereochemistry. That means same stereochemistry. Okay. Or no change. To remember this, you just remember cone and you just think in your mind whatever happening in cone will be opposite to whatever happening in this. Instead of by hearting this, you take this C for change. C for change. So cone means change. Okay. So C cone means change in stereochemistry. Now we'll take a molecule and explain how the product will come. For that, again, I'll take the molecule that we described earlier. Suppose we are taking this molecule. Here it is CH3. Here also it is CH3. Suppose the reaction is happening in thermal condition. What will be the product? So I told you first step is, what is the first step? Determining stereochemistry of the reactant, right? How to determine the stereochemistry we already learned. We'll take the reactant molecule. First, we'll look at one bond, this bond, and we can see one bond is this direction, other bond is this direction. So it is trans. Now look at the second bond. Here, one bond is this direction, other bond is also in opposite direction. So it is like trans. So both trans comes means what? If both trans are coming, that means overall stereochemistry is cis. So now we got the overall stereochemistry of the reactant. Now what is the second step? Second step is determining whether cone or disc rotation is happening. That is our next. We need to determine whether cone or disc is happening in this molecule in this mentioned thermal condition. For that, we need to know what type of system is this molecule, whether it is foreign system or foreign plus system. We need to see. Suppose this molecule is participating in electrocyclic reaction. We are taking the molecule here. Suppose this molecule is participating in electrocyclic reaction. How the reaction will proceed? This will move through here, this move to here, this will move to here. So product will be here one new bond will form, here also one bond will form, here also one bond will form. Okay. Now we are determining the stereochemistry. Like here, one bond will be towards us. Here one bond will be towards, here one will be away from us. However, the CH3 will come is what we need to determine. Okay. So look at the number of bonds here. To know how many electrons are participating in the reaction, we can also look at the number of bonds, number of arrows here. 1, 2, 3. 3 arrows are there. That means 3 pi bonds here participating in the reaction. That means 3 pi bonds means what? In each pi bond, 2 electron will be there. 2 electron into 3 pi bond means what? Total 6 electrons are participating in this reaction. So 6 electron is an example of what system? 4n plus 2 system. So this is an example of 4n plus 2 system. Now we'll go back to the selection rule that we already know, which is that 4n delta is cone. This is the relation we already know. So now we need to find in 4n plus 2 system, in what condition? Look at the question. In thermal condition, which rotation will happen? That's our next doubt. So for that, we'll write a relation. Right? We have two systems. Either it can be foreign system or a foreign plus 2 system. And there are two conditions. Either it can be thermal condition or HNU condition. The thing that we already know is foreign delta cone. So foreign delta cone means in foreign plus 2, the opposite will happen. In thermal condition, it will be dis. So here, what rotation will happen? This will happen. This also we got. And what is meaning by this? I told you here, cone means what? Change in stereochemistry. So this means what? Same stereochemistry or no change in stereochemistry. So we are taking reactant molecule. We already got it as this. Now this molecule is undergoing what rotation? This rotation. This means what? No change in stereochemistry. That means stereochemistry of the product will be cis again. Now we'll draw the stereochemistry of the product. How we'll draw this? We'll take this molecule here. Since this means what? Both these substance will come on the same side. That both CH3 will come on the same side. Here it will be hydrogen here. Normally we will not mention, we will not denote hydrogen in a reaction. So we can just remove the hydrogen. So the product will be kind of like this. So we got the product in this reaction. Now we'll discuss, before going, I'll tell you, the first step is determining the stereochemistry of the reactant. Next step is determine whether cone or disc is happening through our selection rule, which is foreign delta cone. And if cone is coming, that means a change in stereochemistry. And disc is coming means same stereochemistry. So thereby we are determining the stereochemistry of the product. Okay. Now we'll discuss maybe 1 or 2 questions, previous year questions, which is asked in CSIR NET, and we'll determine the end product. Okay. So first look at this example. The major product formed by photochemical reaction of 2E, 4Z, 6E, deca-tri. Deca means what? Deca means 10 carbon. Tri means 3. Ene means what? Ene means double bond, right? So deca-triene means there are 10 carbon atom in which 3 pi bonds are there. So first we'll draw the molecule. 10 carbon atoms are there, right? So we'll draw it as 1, 2, and 3. In 3, No, actually in 2 itself, a pi bond is there. So between 2 and 3, a pi bond is there. And that is E. E means what? E means trans. Z means cis. So this pi bond is trans. Now 4. In 4, again, 1 pi bond is there. That will be cis. So this bond will come here. Now 5, 6. Again, look at 6. In 6 again, one more pi bond is there. That is what? Your Z. That is E. That means trans. Then 7, 8, 9, 10. So our molecule is like this. So as you can see, it is a, what we told about electrocyclic reaction. It is a cyclization of conjugated polyene system. So here cyclization can happen, right? It is a polyene system, which is containing 3 pi bonds, and also it is alternate single and double bond. So here electrocyclic reaction can happen. Now, to know the stereochemistry, we need to draw this in another way. We cannot change the stereochemistry. All the bonds that are cis, we need to draw it as cis only, but we can modify, we can draw this in another way, which is like, first we'll draw 4 and 5 bonds here. Now, we'll draw 3 here, and 3, 1 pi bond is there to 2. And in 6, 1 pi bond is there to 7. Okay. In 3 and 2, it is trans, so this bond will come here. And in 6 and 7, pi bond is also trans, so this bond will go here. And it is 8. Now 9, it is 10. Now we can do the electrocyclic reaction here. How? This bond will move here, this bond will move here, this bond will move here, and we'll get end product like here, 4, 5 will be there, and 1 is there, 1 is here. Here, 1 new bond is being formed between 2 and 7, and between 4 and 3, 1 pi bond is being formed. 5 and 6 are also 1 bond is being formed. And here, 1 substituent is here, and here also 1 more substituent. Now we need to determine the stereochemistry of these 2 substituents. That is the only remaining work. So to do that, we look at the condition. It is happening in, question itself is given, it is happening in photochemical condition. That is H nu. And look at the number of pi electrons. It is participating in this reaction. 3 pi bonds. That means 3 pi bonds means what? 6 pi electron. That means what? 4. It is a 4n plus 2 system. Now we need to go. So what we need to find? Here we already got, it is a 4n plus 2 system. It is, reaction is happening in what? Photochemical condition. We just need to get what will be the stereochemistry of these 2 bonds. To know the stereochemistry, we should know whether con or dis is happening in this reaction. To know that, we need to look at the selection rule, which is 4n delta con. Again, we'll draw here what? We have 2 system, 4n system or 4n plus 2 system. Reaction can happen either in delta or H nu. We already know 4n delta con. We need to find out this. What will happen in 4n plus 2? H nu is, we need to find. Okay. So in 4n delta con means 4n plus 2 delta, it will be this opposite of con. It will be this. So, and again, 4n plus 2 in thermal condition, this is happening. Then in H nu, the opposite of that will happen. What will be that? It will be con. So we got what we are looking for. Here, con will happen. No, we know what is con means. Con means C is standing for change. Con means change in stereochemistry. So con means change in stereochemistry. We look at the stereochemistry of the reactant molecule. Here is our reactant molecule. We need to look at the both bonds, this bond and this bond, and determine the overall stereochemistry of the bond, of the molecule, reactant molecule. This bond, one substituent is this side, other one is this side, so it is trans. Here, this bond, one is this side, another one is opposite side, again it is trans. So I told you trans means what? Cis, right? So overall stereochemistry is cis, and this molecule is undergoing what rotation? Look here, it is undergoing cone rotation. Cone is standing for change in stereochemistry. That means in product, it will be, cis will change to trans product. Now, the only remaining job is drawing the trans product here. How will draw? One bond will be towards us, other bond will be opposite to us. So now we look at the, so this will be the answer. We'll get another doubt here. There were two possibilities. Either this molecule can undergo electrocyclic reaction, as we mentioned, like this bonds can participate in reaction, like we already mentioned. This bond and this bond and this bond. That time we'll get either this product or this product. But you may think these 4 bonds can also participate. Instead of participating all 5 bonds, instead of taking part all these, we can only consider the reaction between these two also. In that case, this or this may form. But you may think why we took only 6. The reason is that if there is a, if in a reaction, if there is 2 possibilities, like for 6, if a product is forming of 6 carbon, a cyclic product of 6 carbon and a cyclic product of 4 carbon, the 6 is more stable than 4. Okay, here this bond is constrained one. So this, if it is a scenario is arising for where you need to determine whether 6 carbon is forming a bond, a cyclic product, or 4 carbon is forming a cyclic product, you just think that all 6 is always more stable than 4. So this will form. And from these two, we determine through all the selection rule and all, A is the major product. Okay. Now we'll look at one more example and we'll wind up the class. Look at this molecule and heat. They are giving this reaction will happen at heat, and we need to determine how many electrons are participating in reaction and what kind of rotation is happening here. So you look at the product. Just look at the product. This bond is not at all participating. There is no change in this bond. So this bond is not participating in the reaction. So remaining 3 bonds. Remaining 3 bonds means what? 3 pi bonds means 6 pi electrons. That means 4n plus 2 system. 6 pi electrons. So either this or this. C or D is the product. Okay. Now we need to determine whether cone or this is happening. So 6 means what? 4n plus 2 system. So 4n plus 2 system in what? Heat means delta condition. What will be the product? So whether cone or this is what we need to find. For that we will write 4n delta cone. Again we will draw our cone. 4n and 4n plus 2 can be delta or H nu. We know 4n delta is cone. So if 4n delta is cone, 4n plus 2 delta will be opposite of this. It will be, this will be this. So this question is so straightforward. It is so easy. So we got what? We got it as this. So this is the answer.